Good afternoon, everyone. Today I will be presenting on a flow-based decision circuit in automated ships, exploring how low-level digital logic enables intelligent, reliable decision making in a modern maritime system. Let's begin. Introduction to automated ships. Automated ships or autonomous vessels are revolutionizing marine transport by reducing human intervention. At their core, these systems rely on a fast, reliable decision. This is where a hardware-based circuit, especially flip-flops, come into play, ensuring decisions are made instantly and correctly, even in a harsh environment. What are flopped-based circuits? Flopped-based circuits are built using flip-flop, basic memory element in a digital electronics. They store binary states and are used to create sequential logic. Essentially, they help the ship remember and act based on the past events, like a change in a course or a sensor trigger. Types of flip-flop. There are different types of flip-flop like SR, JK, D and H, each with its own behavior. For instance, D flip-flops store the input value at the clock edge, while JK can toggle states. These are the building blocks for creating control logic in automated systems. Role of flip-flops in decision making. Flip-flops act as a memory units in a decision circuits. By combining them with logic gates, we can build circuits that make decisions based on both current input and previous states, perfect for a task like obstacle avoidance or engine monitoring. Why use a flow-based circuit in ships? Ships operate in a remote, sometimes a hard environment where reliability is critical. Flow-based logic is ideal because it's fast, power efficient, deterministic, and doesn't rely on complex software layers that can fail or lag. Basic architecture. Here is the basic architecture. Sensors feed data into logic gates, which includes flip-flop. Based on this, decisions are made and actuators are triggered. For example, if radar detects an obstacle, the circuit might initiate a change in direction immediately. Control flow design in decision module. Control flow in this circuit is handling using state machines. Each state is represented by a unique combination of flip-flop outputs. For instance, a state might represent obstacle detected and another might represent course corrected. Sensor integration. Common sensors include radar, sonar, GPS, and AIS. Their analog or digital signals are processed and interpreted by logic circuits. Before the signal reaches the flip-flops, conditioning circuits clean and shape the signal to ensure accuracy. In which sensor types are radar detects surface, object, and vessels. Sonar maps underwater obstacles. GPS provide precise data. AIS shares vessel position info. In from another, signal conditioning filter and adapts raw sensor data for logic circuits, ensures accuracy and noise reduction before decision making. Case 1, course correction. Let's say an obstacle is detected ahead. The circuit immediately sets a flip-flop which transitions the system to a new state. This state then activates a predefined course correction. No waiting, no software lags. For core collection logics, there are three main ways. First is the obstacle detection, second is memory trigger, and third is actuation. First, obstacle detection have a sensor signals that triggers flip-flop state change. Second, memory triggers, in which flip-flop store decision to alter heading. Third, actuation, in which steering commands initiate new safe course. Use case 2. Engine control. Another application is engine health monitoring. Sensor check for overheating or abnormal vibration. If an issue is detected, flip-flops can trigger emergency shutdown protocol without needing human net override or OS processing time. From which flip-flop in a maritime system, this represents explore in a flow flip-flop circuits for maritime engine control, and from there we can take real-time decisions and reliability. Flip-flops based circuit versus microcontroller. Compared to microcontroller, flop-based circuits are simpler, faster, and more predictable. They are ideal for a safety-critical decision, while microcontroller offers flexibility. Closed circuits are unbeatable when speed and reliability are key. From the slide, we can see clear difference between the flip-flops and microcontroller. There are three major differences: speed, in which flip-flops have ultra-fast hardware response, and from the microcontroller, software execution delay. In the complexity point, flip-flops have simple fixed logic, and in a microcontroller, there are complex program tasks, in which flip-flops have low cost and microcontrollers have high cost. Power efficiency. These circuits consume very little power, ideal for long range mission where energy is limited. They also reduce the need for cooling systems which are bulky and consume additional energy. From this, we can overview the circuit diagram, and from that, a lower program draw, which contains only consume minimal energy during operation, and for ideal long voyages, energy efficient design suit extended maritime mission. Reliability in harsh environment. Slope-based circuits are highly resistant to electromagnetic interference and can handle wide temperature ranges. Unlike software that don't crash or hang, making them ideal for naval conditions. For in reliability in harsh environment, there are three main topics which can be EMI resistance, second temperature tolerance, third physical durability. Real-time decision making in autonomous ships, real-time reaction is critical. Flip-flops respond in nanoseconds without the delays of operating system or a high-level software. This can mean the difference between a safe core correction and a collision. From that, no OS latency, instant processing without operating system delay. Immediate state change. Flip-flops respond the moment signal occurs. Redundancy and a fault tolerance. These systems can be built with a redundancy. If one part fails, another can take over. Error detection logic can also be added to alert for inconsistencies, boosting safety and reliability. For that, parallel circuits, which contains multiple flip-flops circuits running simultaneously for safety. In another way, error detection, extra logic gates identify faults to trigger alerts. That is the cure of this system. From this, now we study case study. Naval USV in a naval unmanned surface vessels, float-based circuit systems are used for navigation, threat detection, and damage control. Reports show significant gain in reliability and response speed compared to software-only models. From this case study, we can see that there are 3 points to learn. Three. First is flopped circuit integration. Second is operational benefits. Third is mission success. These are the three that can be elaborate in the long. Challenges and limitation in design. However, here are downsides. Flip-flop circuits are hardwired, meaning any changes require physical redesign. For complex, flexible tasks, they are not ideal. This is why they are often combined with the program systems. Design complexity often hinders smooth implementation, and systems lack flexibility in handling complex designs. Future outlook. Future ships may use a hybrid system, combining flip-flop based circuit for a core safety function and AI or microcontroller for advanced decision making. This hybrid approach balances reliability with adaptability. In conclusion, flop-based circuits are essential for fast, safe, reliable decision making in automated ships. Their deterministic nature and simplicity make them indispensable in critical maritime systems, in which key takeaways address design challenges by embracing hybrid tech solutions. And we are looking forward for automation trends promise safer and smarter maritime operations.